Chemistry. This lesson is going to deal with how strong and weak acids react when they're in solution together with strong and weak bases. So strong acids, it's a complete dissociation of a proton from the acid to a water molecule, creating a hydronium ion, H3O+. Remember, H3O+, or sometimes we just call it H+, is the definition of an acidic solution, is when they are in the aqueous water solution. Weak acid is some dissociation, not 100% of the protons go to H2O to produce H3O+. Now, when you have excess strong acid with strong base, that means you have both strong acid and strong base in the solution, but you have more of the strong acid, more molecules of strong acid. Then you have a complete dissociation of the proton from the strong acid to the base, the OH-. That happens first until the OH- becomes a water molecule. All of them become water molecules. After that, the extra protons that the strong acid has dissociate to H2O to produce H3O+. Then the solution becomes acidic. If you have excess strong acid with a weak base, it's the same as the situation above. You have a complete dissociation of the protons from the strong acid. First, they go to the weak base until the weak base is neutralized, and then the rest of them go to water molecules to form hydronium ions, and that makes the solution acidic. And we don't deal with weak acid and weak base situations. Okay, first we're starting with the strong acid. We've really already seen this one in previous lesson. Strong acids completely dissociate in water. This means that every strong acid molecule that enters the water will give a proton to a water molecule. So there we drop the hydrochloric acid, HCl, into the water, and the proton moves over to the water molecule, creating an H3O+ hydronium ion. That's what defines an acidic solution. The chloride ion, Cl-, is the conjugate base of HCl. The conjugate base of a strong acid never accepts a proton. In other words, if a strong acid always 100% of the time wants to give away its protons, it doesn't make any sense that it would take one back. So chloride does not change the pH. I refer to chloride, or the conjugate base of a strong acid, as a fake base. Technically, it is the conjugate base of hydrochloric acid because they differ by that one proton. However, since chloride will never take back a hydronium ion, a proton, and that's the definition of a base, that it accepts a proton, then really it doesn't ever act as a base, even though it is technically a conjugate base of strong acid. So I call that a fake base. The water molecule becomes a hydronium ion, H3O+. Here water acted as a base by accepting a proton. H3O+ lowers the pH of the solution. Remember, acids make the pH go down towards 0. Now a weak acid, so that's some dissociation of a proton to a water molecule, producing a hydronium ion. So hydrofluoric acid is a weak acid because it's not one of the 7 strong acids. The reason you need to memorize the 7 strong acids is because if an acid is not one of those 7, then it's a weak acid, and there's tens and tens of thousands of those. When we put hydrofluoric acid in water, only a small fraction of the molecules will dissociate and pass their protons to the water molecule. So there we see 4 of them are dropping into the water. So HF does not completely dissociate. This is the definition of a weak acid. In this example, we will say that 1 out of 4 hydrofluoric acid molecules ionizes and passes a proton to water. The actual number for hydrofluoric acid is actually about 1 in 10,000. So there we go. The proton moves over from one of the hydrofluoric acid molecules to a water molecule, creating a hydronium ion, H3O+. Remember that dynamic equilibrium means that the ionized hydrofluoric acid can take back a proton, and that any other hydrofluoric acid can then pass a proton to a water molecule. So that proton that just got passed can go back, and then the proton from a different hydrofluoric acid can go to the same or a different water molecule. And that's a dynamic equilibrium. But at any one time, 1 out of 4 is ionized, has given up its proton. So the fluoride ion F- that remains is the conjugate base of hydrofluoric acid. A proton can return to the lone pair of a weak acid. Weak acid problems require a Rice table and a law of mass action to compute concentrations because they are equilibrium situations. Next, we have excess strong acid with strong base. That means you have both strong acid and strong base in the water in the solution, but there's more molecules of the strong acid. So that will mean you're going to have a complete dissociation of a proton first to the base, OH minus, until neutralized. We know that a strong acid will dissociate to water, but it would prefer to go to the base. And then once the base is all neutralized into water molecules, then the protons dissociate to H2O to produce H3O+. So here we have a situation in the acid-base section. We dealt with acids reacting with water. It is possible for an acid to react with a base other than water. So here you see we have two hydrochloric acid molecules, which are strong acids, and one sodium hydroxide, which is a strong base. And then down there is a representative water molecule. Sodium hydroxide is a strong base. It completely dissociates to sodium, Na+, and OH-. So there it goes in the water. Okay, your solubility rules tell you that sodium is going to dissociate or break away from anything it's attached to. So the Na+ is a spectator ion. It has no effect on the reaction. And the OH- becomes negatively charged. A strong acid such as HCl is added to the solution. Since it is a strong acid, we know it will completely dissociate. HCl will completely dissociate to both the hydroxide ion and the water molecule 100% of the time. So which of the two molecules would the hydrochloric acid rather pass the proton to, OH- or H2O+? Hydroxide, OH- has a stronger negative charge than H2O. Therefore, the proton would first, a hydrochloric acid would first like to pass it to the OH- to produce, that neutralizes the hydroxide, turns it into a water molecule, H2O. Next, after all the hydroxides have been neutralized, HCl or any acid will dissociate to H2O, water, to produce hydronium ions. Now the solution is starting to become acidic because it has hydronium ions. Therefore, the proton will be attracted to the OH- hydroxide over the water molecule. So what you're going to see is when the H+ attaches to the OH-, it forms a water molecule. Water is a neutral substance with pH of 7. This is called a neutralization reaction, and acids and bases can neutralize each other so that the solution is neither acidic or basic. So here we see the first proton is going to go to the hydroxide, and that creates water, H2O. Then once all of the hydroxides have been neutralized, after all the hydroxides have been neutralized to become water, the remaining HCl molecules will pass a proton to a water molecule, creating H3O+ ions. So there you see that second one is going to go to the water molecule, and now that's a hydronium ion. Now the solution is becoming acidic. So it started off as basic. It was neutralized by the first proton to become water. That's a neutral substance. And then the second one passed a proton to the water molecule to create hydronium ion and make the solution acidic. The H3O+ ions lower the pH of the solution toward the acidic range. The chloride ions Cl- are neutral and do not have an effect on the pH of the solution. Let's be clear on that term neutral. You can see it has a charge to it, a negative sign. That it's not electrically neutral, it's an anion. But it is acid-base neutral, so we have to be clear which kind of neutral we're talking about. Almost always in this unit, we're going to be talking about acid-base neutral. So the chloride ion Cl- is not acidic or basic, it is neutral. The water molecule is also neutral. The creation of H3O+ means that the solution becomes more acidic. So that after the base OH- has all been consumed, the remaining acid molecules will react with water to form hydronium ions H3O+. Now excess strong acid with weak base, it's going to do exactly the same thing as the strong. It's going to complete dissociation of the protons first to the weak base until neutralized, and then to H2O to produce hydronium ions. So here we have a weak base over there on the right, that's ammonia, and then we have two strong acid molecules. Water is a weak base in the presence of an acid. When another weak base is present, it has a greater attraction for the proton, the H+, of an acid than water does. The weak base has a pH greater than 7. In this example, in the example below, the strong acid HCl first dissociates to the weak base, ammonia, to form ammonium, NH4+, that additional proton. After all the ammonia has been consumed, the strong acid dissociates to the water, H2O, to produce hydronium ions. So there goes the first proton. It goes over to the weak base to form its conjugate acid, will differ by one proton from ammonia. That's called ammonium. So strong acid first neutralizes to the weak base NH3, creating NH4+. Then any remaining HCl will dissociate to water, creating an acidic H3O+ solution. The H3O+ will lower the pH toward the acidic range. And finally, weak acids and weak bases we don't discuss. Now we're going to go on and look at base reactions, how bases react in the presence of acids. So we're going to start with a strong base in water. That's a complete dissociation to produce hydroxide ions. Remember, strong bases carry their own hydroxide with them, and they just dissociate like sodium hydroxide to just leave the hydroxide ion behind. That's a strong base. Weak base in water accepts some, usually very small number of protons from a water molecule, producing an OH-. So a weak base does it in kind of a roundabout way. Rather than bringing its own hydroxide OH-, it steals a proton away from a water molecule, and that leaves an OH- behind. That's what's left behind when you take a proton away from a water molecule. But that only happens some of the time. Then you have excess strong base with strong acid, so you have both in the solution, strong base and strong acid, but you have more of the strong base. What will happen is a complete dissociation of the hydronium ions from the acid to the base OH to create H2O. Then, once you run out of strong acid, the rest of the hydroxide ions will just remain in solution and create a basic solution. Then excess strong base with weak acid in water accepts the H+ from weak acid, all of them. Weak acids will totally give up their protons to a hydroxide. And then they're going to do that and produce water molecules. Then the remaining OH- remains in solution to create a basic solution. And again, we don't deal with weak base, weak acid situations. So let's start with strong base in water. Complete dissociation. So there you have a water molecule, and on the right up above you have sodium hydroxide, a strong base. So in the acid base section, we dealt with bases reacting with water. There's sodium hydroxide. It's a strong base because it contains an OH- ion with it. It goes into the water. In water, a strong base will completely dissociate into the metal cation, that's the sodium, and the hydroxide ion. So there it goes. The Na becomes a spectator. The creation of a hydroxide ion, OH- is what defines a base and can react with an acid. The metal cation sodium does not further affect the reaction. So nothing further happens here. It's not going to draw a proton away from a water molecule because that's just going to make that water molecule turn into a hydroxide. So it's just playing ping pong with that proton. It's not going to do that. And now we go on to a weak base in water. It accepts some, usually a very small number of H3O+ or H+ ions from water, producing producing OH- rather. Okay, so here we have two ammonia molecules. They are weak bases, and we're going to put them into water. So when a weak base such as ammonia, NH3, is placed in water, it will occasionally pull a proton away from the water molecule. So we're going to say that proton is going to jump over to the ammonia molecule. The result is the ammonium ion, NH4+, and a hydroxide ion, OH-. In this situation, water acts as an acid by donating a proton to ammonia. So water can be either an acid or a base. It just depends on what it's reacting with. Remember, it's right in the middle of the pH scale, 7. So it can either react with a base and act as an acid, or it can react on the acid side by accepting a proton and becoming a base. It can be either one. It just depends on what it's reacting with. The ammonium ion NH4+ is the conjugate acid of ammonia. Hydroxide OH- is produced when the water molecule loses a proton. Now we go on to excess strong base with strong acid. So now you have 2 sodium hydroxides over there on the right and 1 hydrochloric acid over on the left. So there's more strong base than there is strong acid. So in this example, there are more molecules of strong base NaOH than strong acid HCl. So we're going to drop those 2 in the solution. And of course, you know the first thing that happens is, now we'll drop the hydrochloric acid in. Then what happens is, first the NaOH will be placed in water, and the Na and the OH ions will dissociate. So those sodiums are just going to go off and be spectators. The OH ions will accept protons H+ from HCl 100% of the time. So there it goes over there. It creates a water molecule. It neutralizes it. This creates a neutral H2O molecule, leaving just 1 OH- in the solution. The solution was basic before the HCl entered the solution. It had 2 hydroxides. After the HCl reaction, the solution is still basic, but less so, because now there's only 1 hydroxide ion, OH-. Now we go on to excess strong base with weak acid. So hydrofluoric acid is a weak acid, and you have 2 sodium hydroxides, which are strong bases. So first the NaOH will be placed in water. Okay, so in this example, there are more molecules of strong base, sodium hydroxide, than weak acid, hydrofluoric acid. The NaOH ions dissociate as usual. Sodium breaks away from anything it's attached to, so that's solubility rules. We care only about the hydroxide, the OH- ions. Next, the hydrofluoric acid is placed in solution. The order of this, by the way, doesn't matter. It all reacts the same no matter what order. We're just doing it in a sequence to make it a little clearer. So the OH- ions accept protons of H+, such as a weak acid, hydrofluoric acid, 100% of the time. So anytime a weak acid is in solution with a hydroxide, it will always give up its proton to the hydroxide to create a water molecule. So this creates a neutral H2O molecule, leaving just 1 hydroxide in the solution. The solution was basic before the hydrofluoric acid entered the solution. After the hydrofluoric reaction, the solution is still basic, but less so. 1 OH- instead of 2. Okay, next here we're going to place several weak acid HF molecules in solution with the strong base sodium hydroxide, NaOH. So place the NaOH in the water first. Again, the order doesn't really matter, but we're going to do it this way. And what happens next is the NaOH will dissociate into Na+ and OH-. It is only the OH- that is important here. The hydrofluoric weak acid is next placed in the solution. Now, how many of those protons are going to jump over to the hydroxides over there? 1 out of 4, 2 out of 4. How many of the HF will dissociate into hydroxide ions? Hydroxide OH- has such a strong pull on protons that it will cause 100% of weak acid molecules to dissociate. This means that every weak acid molecule that enters water will give a proton to a hydroxide ion. In the presence of hydroxide ions, OH-, a weak acid will 100% dissociate to a hydroxide, but not 100% to water. That's why it's called a weak acid. This means that a weak acid will neutralize turn to water molecules 100% of the strong base OH- ions in solution. And again, weak acid, weak base, we don't discuss. So that takes care of our lesson on how acids and bases interact. This is going to be important when we get to the subject of buffers.